All right, let's kick this off. Like I was saying, we have a first-time DConf speaker. He's talking about my favorite subject, game development. So please take it away, Lewis.
Sweet. Thank you so much for the warm welcome. I'm Lewis. I'm here to talk to you about the 3D game and engine that I built with D over the last 5 years or so. Yeah, so that's me. I'm Lewis. I'm a video game programmer specializing in rendering. I've been working in AAA worked for about 5 years at kind of a bunch of studios in the Vancouver area, Capcom, EA, and Relic. And more recently, I've been specializing in rendering, which is why I tried to build a 3D renderer from scratch. I would never have attempted that otherwise. Worked on a handful of games that you may or may not have heard of. So the last 5 years has been just me as a solo developer working on a indie game called The Art of Reflection, which is basically a 3D puzzle game. If you've ever played Portal or Viewfinder or games like that, it's kind of in the same vein. Take something interesting or weird about space or time or some concept of the world around us and bend it in some way and see what happens if you make that the new reality, and then build a bunch of puzzles to kind of explore the different parts of that. And that's what this game is. So in my game, it's what would happen if you can just pass seamlessly through a mirror. Let's take a look now, and if the live demo gods are smiling upon us, I think we might be able to actually run around here. Yeah, there we go. Perfect. All right. So this is the game. There you can just kind of imagine the sound effects in your head, just make like swishy whooshy noises and stuff as things happen, footsteps and whatnot. So it kind of looks like a regular first-person thing. The main mechanic in here is that you can at any point kind of zoom in like this and find one of these totems and then press a button and you will teleport to the totem. Doing this kind of like, if you have a film background, you know what a dolly zoom is. I'm doing a dolly zoom in order to teleport you, which is basically correcting the field of view and moving you at the same time to hold a subject constant. And the crux of the whole thing is that, let's run over here. This dolly zoom works in mirrors. So if I zoom in on this thing in here, I just went right through a mirror. Same with over here. Whoop, it all works. These mirrors are like, totally dynamic things. You can pick them up, rotate them around, find another thing, go through it, whoop, you go right through the mirror like that. You might be wondering, wait a second, doesn't that make things like become forwards or backwards or flipped? And the answer is yes. So like this text, you just saw me do it. This text is forward here, and of course it's backwards in the mirror. And then when you go through the mirror, it's now backwards, and that's just like the world that you're in now. Okay. It's like the basic mechanic of the game. I don't know if it's applause worthy. If you put two mirrors against each other, you get these like kind of long infinite reflections like this, kind of like happens with real mirrors. And of course, the sort of zooming stuff works with those. It's a little disorienting once you start to do more. Let's stress test this laptop here and do some like gnarly stuff. Let's kind of get a bunch of mirrors really close to each other so you get a nice hollow mirrors effect. And this should bring the laptop to its knees if I do this right, which is good fun to do in the middle of a live demo. But there we go. Oh yeah, look at that. But you can see the frame rate taking a little bit of a dip, but like it's broadly working. Again, you can just like pick any one of these and kind of go whoop like that, and pull it out and see what we were dealing with. It was just a bunch of mirrors facing each other. I kind of explore this sort of mechanic in a whole bunch of weird ways in the game. Let's see how well I know how to play my own video game here. If I go up into this area here and drop down over here, zoop. So if you have a mirror, you see I'm adding my own sound effects. If you have a mirror in the floor here, you can see that it kind of like reflects, everything gets reflected vertically instead. And so that's what I do with gravity. So it looks like this box would be upside down here. And so if I pass through this, now that upside down box means I'm falling towards the ceiling and I'm now on the ceiling. And there's that box, where is it? Way up there. And I can spot it down here in the mirror, and I'll go through this mirror. And now I'm falling back towards the floor again. And so I, use this sort of thing to just explore all sorts of weird stuff with the mirrors. As always, with infinite looping mirrors, it kind of just works like that. Anyways, that's the game. I do a whole bunch of puzzles and kind of in-world and out-of-world, or in like puzzle chambers, kind of like Portal, but then also just like integrated into the world. Some other stuff was just a variety of puzzles throughout the game. So now let's talk about how I did it and why I chose D for this project. At the very start of this project, I had a bunch of technical goals. Basically, I needed to support this kind of central mechanic that I'd envisioned, and I needed to make sure that I could get it to work properly and that I could get like the detailed graphics work to work properly. Like when I first implemented the passing through the mirrors, there were like 8 or 9 separate bugs that caused like a flicker or a hitch the moment that you pass through a mirror. And I needed that to not be the case. It needed to be totally seamless. So I needed something that would give me the control to be able to do that. I needed to support lots of mirrors and lots of reflections. It couldn't be an edge case to have a mirror on the screen. It had to be just like constantly okay. And I needed to be able to drop 5, 6, 7 mirrors into a level and not worry about performance. I needed to hit 60 FPS because that's the gold standard in video games. And I wanted to support reasonably old machines. This laptop I got it used in 2020. It's like a GTX 1080. So it's not like a top of the line graphics card or anything, and it's running this decently well at 1080p. I've gotten reports from other people that it seems to work pretty well on Steam Deck or on other like somewhat lower end machines, which was one of my goals. In terms of process, one of the big things that I came away from AAA, I learned a lot in my time in AAA, and it was a really good experience learned a lot from a lot of really smart people. One of the things that I came away with was that a slow iteration time really sucks. Sometimes it was as bad as like 25, 30 minutes for a recompile on some of the really big projects. And that is really bad for your ability to get stuff done. And also just your happiness on a project. And so I wanted to come into my own project being like, okay, I'm shedding everything. I'm building all my own stuff from scratch. I'm going to make sure that iteration time is this pillar that I am not going to sacrifice on. And so that was a really big goal for me. I'm one person doing this, trying to build a kind of complicated thing. And so I need to do the simplest possible thing that I can at every step of the way to just be able to move on to the next task. I'm not trying to build a general purpose engine. I'm not trying to support every possible variation of this game or any game. I'm building the code that supports this game and this engine, full stop. I needed to make sure that I could dive in and fix or customize things as I need to. It's just been my experience developing like projects that are going out to an end user, is that like I need to make sure that I can have enough control, because like the buck kind of stops with me. Like if like there's a bug in the project, I can blame some library I used or whatever, but like that doesn't work for the customer or for the person who paid for my game. I have to be able to say like, nope, I've got it, I'll fix this. And so I need to give myself control technically to be able to do that. And then finally, I've worked on this project for almost 5 years now. And I want tooling and stuff that I'm going to be happy using. If I'm not going to be happy with it for 5 years, then that sucks. That's a bad sacrifice. As for why I chose D for this project, I mean, I had the very rare opportunity to get to start from scratch, which is why I was able to even make this choice at all. Usually you're stuck with old legacy C++ code and you're just building on top of that. A lot of the stuff I wrote here is like were things I was considering as I did this, but they're all the stuff you're familiar with, so I won't waste time on them. Just kind of all the features of the language that you all know and love at this point. I want to highlight a couple that you probably also know, but are not always talked about as much. The blisteringly fast compile time of DMD, as Walter was talking about earlier, is one of the key things it was a huge selling point for me when I was choosing D, because it fed into the iteration time thing that I was really trying to prioritize. The fact that D is a mature language that's been around the block and it's gone through a lot of revisions, a lot of iteration, a lot of stabilization and bug fixing and robustness passes, was huge for me. And then it also means that it's got lots of libraries that have been built against it, which was something I needed, because I'm not building literally every single thing from scratch. I'm using all sorts of middleware and other game libraries and things like that to make this work. And just the flexibility of D was a huge selling point to me as well. Just like knowing that I could kind of like go ahead with the project fearlessly and not have to worry about like getting backed into a corner by the language. I had a lot of confidence from my early experimentation with the language that if I needed to get something done, D would let me do it. If I needed to do raw pointer arithmetic somewhere, I could do it. If I needed to circumvent the garbage collector, I could do it. If I needed to drop into assembly, I could do it. And so like whatever I needed to do, the language was going to let me do that. And then interop with C and C++ is mandatory, just because of all the different libraries that we use. So the way that I've ended up kind of like landing on using D for this particular project is just really like keeping it really, really simple. I do a lot of plain functions and structs and just like a relatively C-like way of writing things, just hopefully a little bit less error prone, thanks to the nice features of D and the stuff that it lets me do. But really, really straightforward. I do basically no exception handling, with very few exceptions, very few classes, honestly, which is kind of wild for some people to hear, I've learned. But just like a lot of really plain structs with very simple, like maybe one level of inheritance hierarchy, or like, like a struct within a struct or something like that. But just trying to keep my data layout and stuff really, really simple. I use templates, compile time, function execution, and traits because they're super useful features, but I use them very judiciously, mostly because I don't want to run the risk of bloating my compile time. So I'm always paying attention and making sure I'm not accidentally doing something that's going to make the compile time go up. And also just because it's easy to accidentally, particularly with my relative noviceness with that sort of code, easy to write something that's like really complicated and really hard to read or debug. And so just like where I can keep things simple, it's good. But then there's just like some features where CTFE and templates and such are just so profoundly useful and let me do something so quickly or so ergonomically that like I can't ignore them. They're such useful features. Basic structure of the engine, I'll just kind of skim over it because it's not all that important. But basically, the game is a bunch of global systems. Again, this will make object-oriented folks wince, but that's fine. This is the way that I ended up doing it, and it ended up working very ergonomically for me. Basically, each system gets data allocated however that system wants. It can be in the garbage collector, it can be not. I'll go over memory in a little second. They opt into game-wide functions like update, draw, and handle events. So say the entity manager can run entity manager to update when everybody is updating. And they just opt into those. They present a public interface to all the other systems who want to use them for something. And the systems call into other systems freely, and they're all global, so they just make global function calls. There's really nothing to it. I don't use event systems or registering for callbacks or observer patterns or anything like that. It's really just like the system calls into the other system. Big advantage of this is that I can see very clearly when I am doing something I shouldn't be doing. So if the physics system is like telling the music box system to do something, I'm like, wait a second, that dependency is sort of not a great idea. And I see it very clearly in my code because I will, in the music box system, see, like physics system dot send it some information or whatever. And I'm like, wait, that shouldn't be there. So it's really easy to just see at a glance where the connections are. In terms of memory management, the GC is something that comes up a lot in games as a worry that people have about being able to ship a game with garbage collected language. The way that I ended up settling on this was that I used the garbage collector basically for like static global, not quite static, but like global and permanent memory. So I do a lot of like garbage collector allocations right at the start and just kind of like pile a whole bunch of things in right at startup for the game and allocate a whole bunch of memory. And then I really don't touch a lot of it for a long time. So it turns out that in games, there's a lot that you load at the start, and then you just kind of leave it all loaded there. And so that's basically how I landed on it. I allow myself to freely use the garbage collector for startup code, for debug, and for tools. My level editor and like material editor and other stuff like that is all built into the same executable. And so they're all in there just like behind debug guards. And so for all that code, I freely use the garbage collector because I don't care about a hitch. It's fine. And then in regular gameplay, I forbid that sort of GC churn, and I force myself to use a couple of simple structures that I've used or just like other means of allocating things that won't run into problems. I don't really use no GC very much, mostly because it's very restrictive. It totally makes sense for applications where you need like a really hard line that there is no GC usage and something. And it turns out, kind of to my surprise as building this, is that I actually don't have as hard a line on that as I thought. Like it's okay if I have a really occasional allocation or like a random edge case or like one hitch every 3 minutes of gameplay is like honestly fine. You can ship a game with that. I just can't have garbage collector churn. Like I can't be using the garbage collector every frame to do stuff. And so no GC ended up being like, it was a very restrictive line. So like, for example, you can't index into an AA with no GC active as far as I'm aware, and I was testing at least even with DIP 1008. That is more restrictive than I needed. What I ended up doing instead was just added some debug printing. There's already some stuff in the GC there for that. So I just added debug printing so that at runtime, I can run around the game with this turned on and just look and see like, oh, is anything popping up? And if I'm seeing anything popping up, I go find the source, fix it, I make sure that it's not running at runtime, and then I kind of leave the rest. And that worked pretty well for me in terms of just like getting garbage collection out of the main like second to second runtime of the game. So I'll go over a couple fun features here that I kind of built into this engine. This was one that was kind of like the first really big example to me of like where D is shining and is like helping me build stuff really fast. This was a thing that I kind of built on a whim to just be able to look inside the GameState, which is the master struct that has a bunch of substructs in it for each system that is like all of the data that is live in the game at any time. It's like organized by system. And so what you can see going on here is that I'm just like poking into different systems and just like editing the values. All I needed to do here was write, it ended up being about 300 lines of kind of like traits code to generate this UI using ImGUI. And then I suddenly have access to everything here. If I add something to the game state, it's added to this UI, and I can just like change or view all sorts of stuff at runtime. So I barely need to like use logging anymore to monitor stuff that's happening at runtime. I just literally open the game state inspector and just take a look at the values as they're changing, and can like run around the game and watch, okay, when I press pause, does the pause checkbox appear? Okay, yes, it does. And if I want to unpause, I can literally click that checkbox and the game unpauses. And it all just kind of works. Like none of the stuff that I'm doing in here were features that I wrote to be able to add a scrubber for the physics time or add a pause checkbox here. This is just naturally emerges from building this like 300 lines of code basically. And this was huge. Like this was the sort of thing that made me go, oh, like, all right, this is why I chose this language. And this is like what I am getting, because I'm paying a small cost, doing things a little bit differently than the industry standard, but this is what I'm getting in return. And it's huge. And it kind of represents like this sort of confluence of features almost. Namely, it's like a really, really good showcase of the D introspection and how easy it was for me to write this. It was like half an afternoon, I think, to get this all working. It was super fast. And ImGUI, which allows you to have this like really scrappy, like one-liner UI like this, which lends itself really well to this sort of thing. And then code hot swapping, which so like I can hot swap in if I'm adding or changing a few things in the state. As long as they're simple enough that they don't break the hot swapping, I can hot swap in new things and they'll show up in this editor, which is great. The Scrapheap is a linear temporary allocator that I wrote. That's a really common technique that people use both in games and out of games, where you just build this like allocator that just bumps a pointer, and then whenever you realize you're done, you just set the pointer back to the bottom and erase everything. And it turns out the frame boundary in a game is a really great place to do this. And so just like you generate all sorts of like scrap memory during a frame, and then just at the end of the frame, you reset it all. And as long as whoever's using it was careful to make sure that nothing needs to outlive this frame, you're good to go. And you can just allocate all sorts of stuff and do lots of really ergonomic processing in this way, the way that you might normally with a GC and feel like you're forbidden from doing it in a game, but because of this, you can do it in a game. I feel like maybe the slightly notable part is that you can see the way that I've set up this mix in here. I basically ended up doing this sort of scoped-based thing where I added a little bit of a hack into the GC proxy, which is internal inside DRuntime, to let me kind of store the current allocator, whether it's the Scrapheap or the GC or something else. And then I can just make this one call and it switches to a different allocator. I do whatever I'm doing and then it switches back at the end of the function. Like it helped me a lot for if I had like runtime code where I was like, this can't use the garbage collector because it will allocate. Sometimes I could just like drop this one-liner in and suddenly it's using the Scrapheap. And because it's all temporary, it's fine. No problem. Hot swapping. Okay, so I mean, in this demo, I think what I do here is I comment out the entire section of code that does the like transparent render. And then once it recompiles, the glass disappears and the particles disappear because they're part of the transparent render. And so like I have hot swapping in this game. I'm using the DLL approach where you put like 99% of your game and engine basically inside a DLL, and your executable is just a super thin layer that basically lives to load the DLL, call a single function on it called game update and render over and over and over and over again in a loop. And then anytime it detects that a new DLL has been compiled, it unloads the current one, grabs the new one, loads the new one, and starts calling game update and render on that new one. And that's the way that hot swapping works. I won't go into too much detail. There's like lots of stuff on how you can do this in, say, C++ already out there on the internet. I'll go into some of the D-specific parts of it that I had to figure out. One of the things to be aware of with this approach is DLL statics. Obviously, when you hot swap a DLL, or you're hot swapping and you're changing out the DLL, things can shift around. So if, say, you had a string constant and you were holding a pointer or a slice to that string constant, like right there in the DLL, that could move, and that will invalidate things and cause you all sorts of headaches. And so the solution that I do is the gnarliest, nastiest solution I could possibly think of. I call .dupe on all DLL statics. Like literally, I just run through my entire game state again with like traits kind of style code, and I find everything that looks like it could be a string constant or some sort of static or an array that was constant, and I call .dupe on it. If you're thinking to yourself, that sounds super wasteful and slow, you're right. But hot swapping is a debug feature, so I kind of don't care. All of the hot swapping is compiled out in release. The whole thing is just one executable in release. The hot swapping is all a debug feature for my own iteration of my own work. And so ends up being like 0.2 seconds or so to duplicate all this stuff, and a little bit of kludgy code is actually not that bad. And this, in my experience, works very stably, despite it being kind of messy and imprecise. Considerations with DRuntime. I've heard rumblings that there might be alternatives to this or work in place, or maybe LDC behaves differently on this regard. And I'd love to chat with some people about this because I feel like there's probably better ways that I could be doing some of this. But what I was reading about or like experimenting with, it seems like when you build a DLL in D, it gets its own version of the DRuntime, which means I have 2 DRuntimes, which is not ideal because that means 2 garbage collectors, 2 sets of internal understanding of what my live threads are and stuff like that. And really, this whole thing is basically acting like one executable. But the solution is pretty straightforward. Again, because this is debug, I can get away with slightly hacky things. I have a bunch of function pointers that get filled out by the executable that are the calls to things that I want for the DLL to be piping back over to the executable, so that I can have the DLL stuff, which is 99% of the game's code, use the same DRuntime as the executable is. And that way, everyone is using the same DRuntime. Everybody is happy. There's a bogus garbage collector that is sitting unused over in the DLL, and that's fine. It's slightly wasteful or a little weird, but again, it totally works and lets the hot swapping continue. And that, like, I only needed to do it with it's like 8 or 9 function calls. It's some basic threading stuff. The GC, and the GC is actually really convenient because it already has the GC proxy built into DRuntime. And so I just use that proxy to pipe stuff over and a couple of other things. And then everything is using the same stuff, and there's no problem. Classes, I don't use that many classes to begin with. So I actually only implemented this like year 4 into the project when I finally was like, okay, there's a couple spots a class would be really useful. VTables and class info sit in the DLL statics because they're in the data section of the DLL. And because they're in there, when I hot swap a DLL, they might shift or move. And that's a problem because your VTable pointer inside of a class might be now pointing to trash. And so I need to deal with that. And so the solution that I ended up with was manually registering the small number of classes that I use with kind of a little templated thing that basically manually does a patch up when it gets created to point to an alternate version of the vtable. So basically what I do for that is I have the data section of the DLL, which has all the vtables in it. I copy those off into a separate storage that is stable and will outlive a hot swap. The vtable pointer for a class by default points into the data section. When it instantiates, I change it so it now points into my vtable storage, the copy that I made. When I hot swap, the DLL data section goes either like gets all mixed up or moved or is invalidated basically. It's fine though because I'm pointing at the known good version inside the vtable storage. And then on top of that, even if I made a change to say that class in the hot swap that would affect the vtable, I copy everything over again on Hotswap, but to the correct location that is fixed in memory. And so because of that, it gets all of the new information in the right location and is already pointing to the right place. And I don't need to worry about trying to find the new place. And classes then work with Hotswapping. All right, into the gnarlier, kind of more detailed stuff about like the renderer itself and the stuff that I had to do to get the game itself working. The mirror rendering in general is broken into 3 steps. Step 1 is pre-draw, which is basically like do the preparation work to figure out what do we actually need to draw here. What it does is it figures out all of the mirrors you can see from the main scene, and then all of the mirrors each one of those mirrors can see, and so on and so forth. And it basically builds a hierarchy out of that. I'll show you what I mean. You can see there's like the main view, and you can see some mirrors, and then mirrors within those. And so the top level mirrors are the first level of children in the tree, and then each of the children within those mirrors is the next level of children, and so on and so forth, kind of going down the line there. And so you end up building this tree. And in order to render this, we walk this tree depth first and kind of linearize that order. And that is the order in which we need to render things. The nice thing about visualizing this or thinking about the rendering needs of these like recursive mirrors as a tree is that you can think about things like pruning off branches of the tree. So like really, like one of the things that I do very aggressively in this stage is I try to figure out, can I really see that mirror from here? If I can deduce that the answer is no, I can like carve out entire branches from this tree and save myself a whole bunch of rendering time. Because each one of these mirrors not only renders a bunch of objects you can see in it, but also renders other mirrors, which in turn renders other objects. So any pruning I can do here early is a huge savings. I'll note, I might even do this accidentally, mirrors and portals are almost identical to implement. My internal renderer or like main file for this is actually called the portal renderer. Literally every portal instance I have has a bool on it that's just is mirror because it's so like they're so similar. Like you can basically think of if you imagine it like an entrance portal and an exit portal, kind of like in the game, if you take those, put them on top of each other and kind of like flip it around and then do like a swap along X, you have now turned your 2 portals into a mirror. So they're like really basically the same thing. And so I support both of them in the game. And like kind of almost hilariously, I use portals, but not for puzzles, just for like moving between different worlds. I had someone describe that to me as like a flex that you have portals in the game and you just don't use them for any puzzles. But I'm like, yeah, no, the game's about mirrors. We'll do that. The second phase of the mirror rendering is the parallel call. This is like, okay, we've got all these mirrors and they each need to figure out what you can see in them. That process broadly in rendering is called culling, which is basically saying, okay, there's a list of all of these objects that I know about. What can I see within those? Or what are we going to actually be able to see? What do we actually need to render here? And you take your view and you like ignore objects that are outside of the view. And this process is one of the only times in the render generally in a game where you have to touch every single object that's in the game. You go through every single one of them, you check them against what you can see, and you eliminate the ones that you can't. And then from that point onward, you only care about the ones that you can see. So it's usually this is a really, really, really tight, highly optimized loop in general in a game because you have to touch so many objects every frame. And so I have to do that for each mirror that I can see because each mirror has its own separate visibility list of what I can see. If you imagine I stand here, I see all the things in front of me, but if there's a mirror here, that mirror sees things behind me. So I need to have separate lists for those. And so I end up like for each node in that mirror tree, I end up with a separate job that I have to do this culling. And I run those all in parallel. Basically, I break up those work and I run them all at the same time because they're completely independent pieces of work. And they all run through the entire entity list and figure out what you can see. The other optimization that I do here is that for a mirror, what ends up working out really nicely is that if you imagine like a mirror Like if I'm thinking of that laptop screen as like a mirror I can see from here, my view might be this, but in reality, what I can see through the mirror is that. It's a really, really narrow field of view. And so what I do is I basically like take my field of view and narrow it to the bounds of each mirror. I did not invent this technique. I think this was invented for Portal. This ends up being a massive savings. This was like the difference between having like 3 to 5 mirrors on screen and having like 100 at once. This one optimization, because it just cuts out so many objects that you would otherwise need to render. The final stage is the stage where we actually make the draw calls and actually render everything out. Basically, what I do is I take the mirror hierarchy, as I mentioned before, I run it in depth first order and kind of like run it for a little while and then stop and call that like a chunk of work and then send that off to a thread. And I have all these threads that run this kind of drawing work in parallel. And I do some like very, very coarse load balancing to try to roughly estimate how long each chunk of work is going to take so that they can all finish close enough to the same time. And we basically go off into another thread, do all of the work to like switch our view into whatever the current mirror's mode is, put our camera in the right place, do some stencil buffer and depth buffer shenanigans to like say, okay, you're only drawing within this little window in the screen, and then render all the objects and then move down to the next level of portals and so on, or portals or mirrors. Yeah, and I break this all up and issue these draw call, or not issue them. I build the command lists for these draw calls, basically like prepare the drawing work for the GPU, all in parallel. And then at the very end, they send their work when it's done back to the main thread, who then submits them to the GPU in the correct order. Not in the order they came in, of course, because who knows what order they come in, depends how fast the threads run, but in the correct order to render the scene properly. There's probably a whole bunch of stuff that I could do to do this even better. I just at some point was like, it got good enough that I could ship the game on it. So I was in the, my principle of keeping things simple. This is the most complicated part of my code base by far. And so at some point I was just like, all right, I'm done with the tech stuff. Let's start shipping this game now. One possible thing that I could probably do is occlusion culling, which basically means if there's a big object like a wall in front of me, you don't need to render anything behind the wall. I don't do that in this game right now. So like if you're staring in front of a giant mirror like that, I am both rendering all the things you see in that mirror that are behind you, and also everything behind that mirror, and then it's just getting wasted because the mirror is in front. And it turns out to be still fast enough, even with that, that I'm not running into too many problems. And so you could probably implement that and get some pretty good savings. I don't do that sort of thing right now. The work that I do right now to try to prune levels, like figure out, can you see a mirror at a particular place on the screen? That work is coarse. It's like a CPU side approximation of what the GPU would actually do to figure out where everything is and figure out whether you can actually see a mirror or not. I basically like do some geometry with an oriented bounding box and the scissor rect and some other stuff and compare them against each other. Really the closer thing to the ground truth would be to like pretend rasterize these mirrors to a really low resolution texture, just to see how they overlap and what pixels end up getting like flicked on basically for every mirror. And if any given mirror affected no pixels, then I don't need to draw this or any of its children. That's like the perfect test. And that's what actually gets done on the GPU side when you are rendering stuff in order to do it correctly. But if I did it on the CPU side, I could save the GPU from doing all this wasted work. But I don't, and it's still fast enough. One thing that you could do is you could move the culling and the mirror pruning to the GPU. I've heard of people doing GPU side culling in AAA games where all of that work to figure out what you can actually see happens on the GPU, where you can then there's a lot of stuff that you can do more easily when it's over on that side. For example, when you're making your decisions about what you can see, you can leverage information like what's in the stencil buffer very easily from over in the GPU, whereas over on the CPU, you have to get information back from the GPU, and that is really slow. You have to stall the whole GPU, send your information back, and then start sending commands to it again. And that is super duper slow, and so I don't do it. But if you did everything on the GPU, you could probably bypass that. And it would probably be a huge savings. And again, didn't do it because at some point I was like, it's been 5 years. I need to ship this video game. So, okay, the actual effect of passing through a mirror. This was like the kind of the most fun thing for me to discover because I had no idea if this would work when I started. I just played around with it a bunch. So here you can see, like, this is what it looks like from first person when you go through. It should look totally seamless. Like there should be no bridge. But if you watch that kind of yellow box there and it bounces there right in an instant, that's what's actually happening behind the scenes. This thing where one of the balls lights up and then the other, that's not something I implemented for this visualization. That's actually what's happening right there. Because the way that passing through the mirrors works is that you fly towards the mirror, and then there's some point when your face is right in a mirror here, that this image and this image are exactly the same. And in that moment, I instantaneously snap your head around and then keep you going out the other side. You basically bounce off of it like a ray of light. And that is how the effect works. There's no two copies of the world. There's no alternate mirrored dimension. It's all the same world. It's just like a visual trick. to make it look smooth as you go through the mirrors. There are a couple things that you have to do, of course, right at the mirror surface. And I discovered all of these kind of organically because, as I said before, there were like 8 or 9 separate bugs that were like, okay, this works, but there's a black flash the moment you go, or there's like a weird depth discontinuity, or an object disappears and reappears the moment you flip your view around. So there were a bunch of things I had to fix. The first thing that you need to do the moment that you bounce off of the mirrors, you have to flip the whole screen horizontally because, of course, mirror image is flipped. And so I do that with just adding a little negative number to the projection matrix to make every pixel go to the other side of the screen, basically, which flips the image horizontally. When you do that, you then have to fix a bunch of other things. So, for example, if you flip the image like this, your controls are now backwards. Left is right and right is left. So I have to invert your controls. When you do that, also any audio sources that are positional, so they're like sound like they're coming from over there, you'll now see that thing over there. And so I have to flip the audio sources to sound like they're coming from the same place that you see them. Like it all basically, once I flip things, I just have to like synchronize everything back up to the way that you'd expect it when everything's been flipped. And then more 3D rendering specific, I have to swap the winding order because when you flip the image like this, you take every triangle that is kind of, its vertices are set up clockwise and you now make them counterclockwise, which in D3D parlance tells it to render it. D3D uses this, and most real-time renderers use this to determine whether you're looking at the front of a triangle and a back. And most of the time, we just don't render the back; we only render the front of a triangle. So that means every object would then become basically inside out, which was really hilarious the first time I discovered it. So basically, I have to tell D3D the moment that you pass through a mirror, flip the winding order for everything, and then flip it back, and so on. And I do the same when you're like looking inside of mirror views. It has to like flip them. Like there's this big like if statement that basically flips back and forth between mirrored or not mirrored based on like, where am I? Am I in mirrored mode? Am I looking at a mirrored thing? Is it a mirrored or unmirrored object inside that? And it just like flips the bool back and forth the right number of times to land on, okay, yeah, you need this winding order. While I say that I built this engine from scratch, I didn't use a pre-built engine. I did use a lot of other code that already existed out there. So I used lots of middleware, lots of open source libraries, and a whole bunch of stuff that was already written for me in D. So lots of bindings and other little libraries and stuff that were like incredibly useful in just being able to get stuff off the ground without having to re-implement entire libraries myself. I wrote my own bindings for a couple of libraries that I wasn't able to find ones for in D. I have not contributed those back yet, but that's like on my to-do list the moment I ship this game. Because some of them are a little hacky right now. I want to polish those up and then toss them out on GitHub or something, or in Dub, just so that, you know, having a binding to the Steamworks API or DirectX text or things could be probably useful for people making games. They were useful for me. And so I'd love to be able to contribute that back, specifically given the amount of other people's code and knowledge and prior work I built on in order to make this game. Like it's like the least I can do. So kind of looking more broadly at my experience in using D for making a video game, like it worked out basically the way that my initial kind of technical inspection led me to believe. The iteration time was great. I think it grew from like 0.5 seconds when I was starting with a tiny code base to like, it's like 5.5 seconds now or something to compile the entire game and engine. My goal was keep it under 10 seconds, and it has been able to maintain that goal very easily. All of the kind of modern features in a better standard library were good. I want to call out as well that the fact that the standard library in D and DRuntime are readable code was huge. So like if there were times where I didn't understand how something was working, I literally just found the source file, opened up the source file and read it, and I could understand what was happening. That was not my experience with like parts of the C++ standard library when I worked in industry. I don't know if any of you have looked at like Microsoft's implementation of like an STL vector or even like a unique pointer. They're wild. They're like thousands of lines of code for something that should be like 50. And so it was really nice to be able to just like really easily understand stuff because it was kind of written sanely. You know, as I was expecting, like D was flexible and capable, and it proved out that I was able to get it to do what I needed to do in the times where I needed to do something very specific. It was like, yep, go for it. It was exactly what I had hoped for. Fixed C++ baloney. You're all familiar with that. The interrupt to C and C++ libraries was magnificent. It worked great. Even when bindings didn't exist, I was able to write them relatively straightforwardly for most things. I'll go over a couple exceptions to that in the next slide. But it broadly worked really, really well. I also want to call out that like D has really good Windows support. And this isn't always the case with open source projects. And I totally understand why. But for me, stuck here in gaming, like we build everything basically on Windows because 98% of our user base uses Windows for games. And so we're stuck using Windows for better or for worse. So having a language that has good support is huge.
I wanted to expand on something when you talked about the incomprehensibility of the implementation of the standard library.
Yeah.
I originally looked at Silicon Graphics implementation of the C++ standard library when I did the original C++ compiler years ago, and I never did figure out how it worked. And I just compiled it and prayed that it would work, and it did. But that was one of the motivating things for creating D is every time I looked at implementations of library code, it was always incomprehensible. And I thought, this is crazy. There's got to be a better way to do this. So, yeah, you've noticed the same thing.
Yep, exactly. Yeah, it was huge. And then the ability for D to let me do low-level access or write a tiny little bit of assembly or do SymD work or whatever else I needed to do, or just like do some really bizarre Windows API call that I need to get the DPI set correctly for the screen or all sorts of weird stuff like that. It was just really easy for me to trust that D would let me drop in and do whatever I needed to do wherever it was, including in a couple of spots, make tiny little hacks or modifications to DRuntime itself to support things like my weird hacky hot swapping implementation and stuff like that. Overall, super glad with the decision. No regrets whatsoever. These are the things that I'd love to chat with people here because I kind of learned a bunch about D as I was experimenting with it and then kind of went into a hole to build the game. And I feel like there's stuff that's probably been either fixed since or improved since, or just I just missed that D supports a particular thing. And so I'd love to chat with people because I feel like there's probably better ways than some of the stuff that I did. Broadly, the fact that C++ name mangling and stuff is supported by D is huge and was really, really helpful for binding to C++ stuff. There were a couple of really gnarly C++ libraries. PhysX in particular does not have a C API and uses inheritance directly in the classes that it exposes to the user. And so I basically had to build D-side versions of those classes and had to get the vtables to line up with the C++ side, which meant sometimes inserting a dummy function for to cover the virtual destructor or something else that D didn't need, but C++ had on their end. I don't know of what the solution is to that. It wasn't actually that hard to figure out, but it's a little gnarly to be lining up vtables and stuff as a regular way of setting up C++ interoperability. But it's also PhysX gave no accommodations whatsoever. It's I think at least a hard problem. There's not a good solution to that I know of. Ecosystem size, everyone knows it's always tough where every now and then I have to roll my own binding or something. That's hard. The only solution, get more people using D, which is part of why I'm up on this stage. I mentioned before the kind of DLL hackery that I had to do for doing the hot swapping. I was able to get it working, which was great. I mean, I'm left wondering whether there's a cleaner approach than what I ended up doing. And again, I would love to chat with people here if anyone has knows of easier ways to do this or ways that are better supported, because that would be super useful and would let me clean up a bunch of my hacked code. Broadly, debugger support was really good and just worked as is in Visual Studio, which was what I was using to debug. Every now and then I'd run into a weird thing, often thread local storage variables didn't show up in the debugger and I couldn't get them to show up in watch windows. And there's a couple other weird bits where it would step over way more code than I thought when I was stepping, and just the occasional bit of weirdness, but none of it was deal breakers. All of it was stuff. And honestly, when I remember debugging stuff in industry and C++, there was weird debugger behavior there too. There was definitely times I remember where it's showing me full on the wrong data, but the wrong data in a watch window. And I'm looking in the memory view and I'm no, I don't know where you got that from, but that's not right. Yeah, so my broad advice for using D for games is do it. It worked great for me. The few things that I was worried about, the fact that it's a more unusual choice than C++ or the garbage collector and stuff, ended up being basically non-issues once I got into it. And it supported me really well in being able to build the game. You can go play the demo now, and the game should ship later this year. That I was actually able to build a thing is hopefully evidence that this language is capable and mature enough for supporting this sort of work. I mean, everyone in this room already knows that, but for anyone else watching, hopefully this is another piece of evidence in favor of that. And then I talked about some weird hacks that I did. You don't have to do those hacks. You don't have to ship a game with DLL hot swapping where you made a tiny little hack to DRuntime or built your own weird swap in allocator thing. That's me doing me stuff. To get things working in a very specific way. You don't have to do that. You can just do the plain stuff and it'll be even simpler on you. That's it. Any questions?
I'm going to jump in first with a comment on that DRuntime and a DLL thing, because that's something I raised in my talk on Quantum Break in 2016. It's been a while. We did have one guy working on it, but, classic open source community thing, he disappeared. So if anybody wants to pick up for that work, please do it.
You told us all the reasons why you picked D for this, but I was wondering how you even learned about D to be able to make that choice in the first place.
That's a great question. It was a while ago, and I'm not sure I exactly remember when I first learned about it. I know that early on, like before I left AAA, I was kind of examining. I knew I kind of wanted to roll my own thing. I actually originally thought it was going to be 2D, and then it ended up pivoting into 3D. But I was examining a few different languages at the time because I was like, I'm frustrated enough with C++ working in industry. There's got to be something better that we've done in the last 40 years. I think I just did like internet searches or was like looking through Reddit or something. I don't exactly remember. And it just came up as one of the languages alongside like Jai, Odin, and a few others. I did like kind of a brief look into each of those. I very strongly considered Jai for a while, but I was like, it's not out yet. I don't think I can wait for it. Sure enough, here we are 5 years later. It's still not public. So I guess that was the right decision. Yeah, no, D was the one that just stood out to me after looking through all of them as being like mature, something that I can reliably like build a foundation on top of. And has what I need to be able to ship the sort of thing I'm looking for.
Cool, thanks.
Yeah, you're doing DLL hot swapping to reload for code reloading for fast iteration, presumably. And I was wondering, how does that stack up compared to just having very fast saving and loading?
Oh, good question. Yeah, one of the alternative approaches, kind of what you're calling out there. Correct me if I'm misunderstanding, is that you can basically like dump your entire game state out to disk. And then when you boot the game and just load that state. That is an approach that can work. One of the downsides of that is that you also need to make sure that your game, you pay whatever your startup cost is in your game every time you boot it. And like you can optimize to get that fast, particularly in a game that's like, I'm not making Grand Theft Auto here. I'm making a pretty straightforward thing with like a total of a gigabyte of assets. Like it's very, very lightweight in general. But even with this, like, even if it's like 5, 6, 7 seconds to boot the game up, you pay that cost every time you do the save state hot swap. And then you also have to build the save state hot swap in that way and figure out how you're going to serialize everything out to disk and back in. I mean, to be fair, I don't think I fully like examined that as a possibility at the time I was doing this. I was just aware of this DLL technique for hot swapping and thought, that sounds neat, let's try it. And it ended up working. I think the save state thing could work. It sounds like there's probably a couple of costs in there. But like if your startup time is half a second, it might be totally viable.
You said you gave up on the no-GC attribute. Yeah. So did I. Are you aware of the -VGC switch, which lets the compiler, while it's compiling, print all the locations where GC allocations happen?
Yes, totally. I'm trying to remember whether, I think I didn't end up using that as much. But yes, that is a super useful tool to have. I think the thing that surprised me the most, like I went into this with the usual game developer mindset that was like, very allergic to a garbage collector. That's just like, no, nowhere, anywhere near my code because runtime, blah, blah, blah. And what I came out with was I think a conclusion that a bunch of people in this room have come away with too, which is that you don't actually have to be that hard line even for games. You just need to like broadly not be generating garbage. Like second to second. You can't be totally naive about how you do memory, but you can have the garbage collector be there and do some stuff and it's fine. What I ran into, like VGC would print out all of the locations and some of those locations would be like in a function behind an if statement that only runs on startup or something. And so it would flag that location and that function, but I'm fine with it being there because it's only on startup. And so the tool that I ended up using mostly was just like print for me actually at runtime when it happens. And then I go run around the world and be like, is anything coming up? Oh, that one. Okay, fix that one. And then as long as it roughly looks good and I don't see any churn, I was happy enough with that. And it seemed to not be generating hitches in the game. So
when you look at something that makes noise in a mirror, the audio location, is it from within the mirror or still the original world position?
So in a mirror, I don't make audio emanate from something that you see in a mirror because that's not how it works in real life either. But once you pass through a mirror and your view is flipped.
Yeah. So about that, I was wondering, doesn't that make like a source just snap to the other ear? Is that?
Oh, I see.
Jarring when you pass through a mirror and suddenly the location of audio flips?
Yes. So what ends up happening in practice? That's actually really funny. I never thought about that problem because I think now I'm thinking about it, I accidentally solved it. So the way that is solved is not in code, it's in design. When you do there were no sound effects because we don't have sound when I was demoing this, but when you do that teleport, there's actually this like really loud blast that kind of happens. This sound effect that's it's just like a bang when you land. And that covers up any transitions that there are, right? And so if something was snapping over, you won't notice because it will be covered by that.
Great talk. Wasn't sure if we touched on the rendering side. Was this Direct 3D 12, and were you using any of the like ray tracing API? And then the other follow-up was, I think I saw NVIDIA's Horizon-based ambient occlusion. Was that something you wrote a binding for as well?
Yeah. So this was all in vanilla D3D11. I used D3D12 when I worked in industry, and my experience with it was that it's a good API for what it sets out to do, and it's more complicated than I need for this game. Basically, like I was confident that like D3D has shipped games for decades, like more than almost 2 decades now at this point. Like I was like, okay, if it can handle those, I'm not going to be developing like literally state-of-the-art rendering tech for this, so I can get away with D3D11 and it's simpler. And so that's what I ended up going with. And yeah, you probably caught it in the binding slide. I use NVIDIA's HBAO Plus or whatever. I can't remember exactly what they call it. And wrote, that one has a really, really clean interface, and they provide a C interface for it. So it was like maybe an hour to get that bound and working in D, and it was really straightforward and worked great.
Awesome. Looks very beautiful. Thank you.
I have a question about the GameState inspector.
Yeah.
Is there a registration mechanism, or you just display what you want to display?
What do you mean when you say registration?
Would your GameState be usable for another project, or the GameState is specialized for your game and it knows this game?
Gotcha. So, I mean, the game state, like the structure itself is specialized for this game. There's some stuff that's probably common for a lot of games, like a counter that's like how much time has elapsed. Like every game needs that. And then a whole bunch of stuff that's specific. The game state inspector itself, though, should work pretty generally, I think, because it literally it iterates at compile time over the struct of the game state and goes through, like every time it sees an int, it generates a little int spinner. Every time it sees a enum, it generates a drop down with all the enum elements in it. And so that, I think, I've not tested it on a different game, but I think that should work without very much change in another game. There might be little bits of customization you want to do. So for example, I wrote a special 5 or 10 line thing for specifically dealing with entity IDs, which is my way of like, keeping track of what entities are here. So it takes that entity ID and like does the lookup to give me an entity pointer so that I can then show the contents of the entity right there without me having to find the other place where that entity is located. That's custom for this game, but you could really easily, like that sort of stuff I wrote in like 20 minutes, basically. You could very easily write that, I think, for a future game that maybe handled its entities differently or had some other weird custom thing it wanted to do.
Hey, great presentation. I'm pretty interested in how you built multi-threaded rendering with directed to 3D11, because I'm more used to doing this with the state-of-the-art renderer, which I guess it's quite easier to do with on older renderer.
Yeah. I mean, D3D12 and D3D11 are the only ones I have direct experience with. D3D12 definitely has better support. It's like built more from the ground up for doing really like high performance, high intensity multi-threading work. D3D11 just like supports kind of the basic version of it, but it turned out to be good enough for what I needed here. Basically, almost all the multi-threading I do, apart from the multi-threading I get for free from things like PhysX and Fmod, I do fork join for everything. So like I don't even have a separate render thread. I literally just like come up to the point where I render, I generate like the work that is needed. I go wide, I pound through that work, and then I go back together and I'm finished the render. And so basically just each one of those worker threads gets a deferred context in D3D11 parlance, and it records whatever work it needs to that deferred context. And then the deferred context is sent back over to the main thread where it then gets submitted to the immediate context. And that's all there is to it. It's like relatively straightforward for the most part, but it's almost certainly not the most efficient thing I could do, but it was enough of a gain to be able to make things generally work. And so that's what I went with.
The game is awesome. I watched my son play it because I don't have a Windows PC, and I'm very jealous that I can't play it. Is there any kind of abstraction that you're doing with the low-level renderer that could possibly be ported to other platforms like Mac?
That is definitely one of the things that my list would love to do. I don't know, I can't guarantee whether I'll be able to get around to it, but it depends on kind of how well the game does and some other financial restrictions. But it's definitely something that I would love to do just because the more people can play it, the better. In terms of like rendering API abstractions, I have a really, really extremely simple version. Like, I do not have a very complicated rendering abstraction. I basically have all of the D through D11 code that is specific to D through D11 put in a separate folder. So there's like kind of a line between the two of them so that if I wanted to swap that out with OpenGL or something like that, the hope is not that it would be seamless, but that it wouldn't be a massive headache. That's like kind of that's like honestly a design goal I've used in a lot of places, which is just like, I'm not trying to make this perfectly interchangeable or perfectly common to everything. But as long as I make it so that it won't be a headache, it will just be normal work. If I have to do this in the future, then I'm fine with that and I go ahead with it. And so like I directly make calls. I don't have my renderer in a DLL so you could change out with an OpenGL DLL or anything like that. But hopefully there is enough of a boundary that I could, with not too much work, carve out that boundary and then re-implement with OpenGL. In the short term, I've heard that the game works well with Proton. So if on Linux, if that works for people, my plan is to, like, I have a Ubuntu dual boot on my computer at home, which I use to test every time I push out a new build. So I make sure that the Proton support is kept. So in the short term, that hopefully should work. But in longer term, I would love to port it to Mac and Linux and other platforms, ideally natively.
All right, I think we're done then. Thank you.
Thank you.